this was, Michael was someone from a completely different community. In our community, now we have yet another guy from a completely different community, Chris Rackauckas. So he is working very closely in the Julia community, Julia programming language. And he's just utilizing the many nice features that the Julia language has and utilize it. They develop the next generation of numerical integrators.
Hello. Yep. Thank you very much, everyone, for, well, thank you, Hilding, for inviting me here. So what I wanted to talk about today was recent advancements that we've been seeing in our differential equation solver software. So what we've really built is this differential equations.jl. So for those who don't know, let me give a quick introduction. This actually started during my PhD when I was looking at methods for high-order adaptive stochastic differential equations, right? I got in my PhD and I said, I want to build the ODE 4.5 of stochastic differential equations. And what I found out to be the hardest part was, how do you know when you actually got it correct, right? So after building a bunch of things for stochastic differential equations, we went back to ordinary differential equations just to find out, like, how good are we building things against C or Fortran methods? And about 3.5 years later, we're still testing that out, right? What we found is that, you know, in order to actually do research in differential equations and numerics, you actually have to find out what are the best softwares out there, and you have to test against it, and you have to really find out which cases are you doing well and which cases are you not. So we had to, you know, find out, you know, let's implement it with MPI compatibility, GPU compatibility, implicit methods, IMAX methods, et cetera, do the whole list of them, and now where are we doing well, where are we not? These are the places that we need to research, and now it's, you know, it started as a research platform, so that way we can implement hundreds and hundreds of methods and understand all of them. But now, because it was implemented in such a way so that way it could be efficient, it became a production platform, and now I know a lot of people in this room are actually using these solvers daily, right? So what I want to actually talk about is not, you know, what is the daily experience of this, but what are the things that we're doing with this platform to further differential equation research. And there are three real major areas. So neural differential equations is the flashy topic we'll start with. A hackable model compiler, which we call modeling toolkit.jl, and improvements to basic numerical methods, right? How can you make a non-stiff solver faster? That's going to be the last thing that we end on. So what I first want to start with is introducing this new field. So I don't know if many people have heard about it, but there's this field called scientific machine learning or scientific AI. I put two of my very recent things up there. So one YouTube talk from JubileeCon 2019 and something that gives an overview of the discipline, what tools are out there for it. And what I want to talk to you about is like what is scientific machine learning and how is it, you know, not just machine learning, right? Because we've had people express the opinion that, you know, machine learning doesn't work in science, and I'll completely agree with you that it doesn't it doesn't work well with scientific problems. So what do you have to do differently in order for it to work well with physics, right? So the way to do that is you have to understand what the mathematical structure of machine learning is, right? So what is the mathematical structure of machine learning? Well, you know, you can just think about neural networks are just a form of nonlinear regression, right? So you say, oh, I want to find out how to fit a function, e to the x. You can try to write it out in terms of polynomials. If you do it in polynomials, right, you know what those coefficients are. You have an analytical solution. You also have analytical solutions for some nonlinear forms. But a neural network is just another nonlinear form where you have no idea what the coefficients would be. It's just, you know, you can find those coefficients with optimization, but it's just another nonlinear form, right? So why is this nonlinear form interesting? And it's because of the universal approximation theorem. So people call this the U.A.T., right? So in a nutshell, right, the quick mathematical thing is you say neural networks can get epsilon close to any Rn to Rm function, right? Just make there be enough layers, make your layers big enough, and it will be an epsilon close approximation to your function at every single point in some compact domain, right? And so in some sense, it's a universal approximator which overcomes the curse of dimensionality. So you can have a very high dimensional function, and you can find a neural network that will fit it using local optimizers, right? There's just so much dimensionality in the parameters that a local optimizer is for some reason able to find a very good fit to that function. Nobody really knows why. Symposium has created a whole new journal for people to write articles about why. But for now, we can just say, you know what, neural networks do this well, right? And so that's why data science and machine learning has worked, because if you treat your model as just, that's some nonlinear function that I don't know, let me try to find it, If you have enough data, you will be able to find a neural network that fits it because of the UAT, right? And so that's our starting point. That neural network can fit anything, which means they probably fit everything really badly, right? Unless you have enough data. So people think about them as a black box, right? But the reason why neural networks have worked is because people stopped using them as a black box. So think about convolutional neural networks, right? ImageNet in 2012 really spawned this second wave, or maybe it's the third wave of AI. I don't know. The other waves of AI were way before I was born. But this newest wave of AI in 2012 was spawned because convolutional neural networks started to do image processing better than any of the techniques anyone had done before. And why did they do that? Well, it's because it's still a black box, but it's a black box that understands spatial structure. Because what is a convolution in a convolutional neural network? A convolution is just where you take a square and you say that this square has to go down to that square, right? So you're basically putting this information into the neural network that pixels that are nearby in a picture kind of matter for each other. Spatial location matters in a picture. And if you put spatial information into a neural network, you suddenly get that image processing works, right? So you can say that, by embedding this information, you can fit images with less data. You still need big data, but you can use less data to make this an actual usable technique. So let's generalize this to scientific structures, right? And so what is the structure of language? It's not, convolutions, it's differential equations, right? So the first example, the easiest one, is just what would a latent or neural differential equation be? Well, you just say that U prime equals F, where, F can be any function, so let's let F now be a neural network. So if F was a neural network, and you had data for what the dynamics were, then what would you do to be able to find the latent function that matches your dynamics? Well, this just becomes a parameter estimation problem, right? So what you do is you iteratively solve the differential equation, you compute the gradient of the solution with respect to parameters, right? So people would understand this as adjoint sensitivity analysis or differentiable programming, and then you would update the neural network parameters and repeat this process, right? And if you do this, if you build a package around this, so we built this package, diffeqflux.jl, for neural ordinary, stochastic, delay, differential algebraic, differential equations, and neural partial differential equations, which we'll get to later as well. And if you do that, then what you get is you get very nice animations. So here I show a 30-line code, which what we do on the left here is we get data from a real differential equation, and then we build a neural network, and then we iteratively solve this equation to get a new prediction from the current neural network. And then each time we solve it, we get the gradient with respect to the current loss function to update the neural network, and then we keep on updating this neural network until over time we learn the dynamics. So if we keep on going with this animation, you'll find that the dynamics that end up being learned will sooner or later match that data. So it's beautiful, right? You have data, and now you can train a differential equation. All you have to do is you have to make neural network libraries embed within your differential equation solver. That's really the difficulty, and that's the differentiable programming part that I'll leave off here. But now you can train different neural networks within the context of differential equations. Now the real power is completely absent from that example, right? Because the real power comes from adding known structure to your machine learning framework, right? That's what we wanted to get to. So let's mix our differential equation with the neural network in specific ways. So what are some applications of this? Well, the first example is, let's say we have dx dt equals neural network, and then dy dt is a linear function, right? The code looks like this. And now what we're able to say is, I know the differential equation for y. I don't know the differential equation for x. Find what that differential equation for x would be given this data. Right? So this is much different than trying to learn the entire data itself. Now you're able to say, well, I have a scientific law for how one thing evolves. I don't know the other. Let's find the other. So what we can do instead is, if we have some chemical reaction network where we know how a lot of these chemical reactions work, we're missing some arrows, we say, what are the unknowns? Well, we stick a neural network on the end of this. You say, here's my model plus neural network. You fit the neural network. And now what are your terms that are missing? Well, what you can do is you can analyze the Jacobian and Hessian of this neural network and find out, hey, this is what it thinks the missing polynomial terms should be inside of my differential equation. And you can try to back out what are the missing reactions from a chemical reaction system. And so what we found and what others have found in this discipline over the last year or so is that this gives you a data-efficient form of physics-embedded machine learning, right? Because the neural network that you need to put in here is much smaller, and it needs to learn a lot less because all of the information that we had from the scientific literature is already encoded inside of the differential equations. So it just needs to learn the missing parts instead of trying to learn the whole system. And so what we found is that we can restate a lot of interesting mathematical problems as training mixed neural differential equations. So nonlinear optimal control can be, well, here's a differential equation system. Here's the function I want to minimize. Now replace your control with a neural network, and now you have one of these mixed neural differential equation systems, and you just use your neural differential equation solver to be able to train that neural network that's in there, and that gives you the neural network that is the optimal control. Right? So this is now, so nonlinear optimal control can be restated as a problem of training a neural differential equation. But there are a lot of other problems that can fall into this as well. So one problem that we see within the current climate model, right? So MIT is partnering with Caltech right now to build the next generation climate model called CLIMA. And one of the things that they do is they take these Boston-esque equations, and then they say, well, we can't really solve the 3D Navier-Stokes model over the entire Earth. That's pretty much impossible for us to do. So what we do is we take small little boxes, and in these boxes, we use an approximation of the Boston-esque equations by parameterizing them to this one-dimensional equation. And so you can get to the diffusion advection equation here by, you basically take the integral in the xy direction to get averages, and when you average out the xy direction, you get one equation in terms of z, but then you have to find out, well, this is a missing function. And then you get another function, and another function, and another function. So you get infinitely many partial differential equations. So what they do right now is they say, well, I'm going to take this function, and let me try to find out what a good one is. And they try to find, what's a good linear approximation? What's a good quadratic approximation? So what we're doing instead is we say, this is a missing function. How can you represent a missing function? Well, you just make it a neural network, and you use your Navier-Stokes equation solver on small pieces of the ocean to be able to train what that missing function should be, and now you have a nonlinear approximation in terms of a 1D diffusion advection equation, and then I think most people in this room can know a fast way to be able to solve it once you're given that neural network. Right? So if you can train that neural partial differential equation, then now you have a fast way to be able to solve Navier-Stokes in this context. Another thing that you can do is solve 1,000-dimensional partial differential equations. So if you tried to do a 1,000-dimensional finite element method or finite difference method, you would probably run out of memory pretty fast, right? 100 points in all 1,000 dimensions. I'm not talking about 1,000 systems of PDEs. I'm talking about it's X, Y, Z, et cetera, 1,000 dimensions. So how could you even do this? Well, one way to do this, this is a very complicated one. Say complicated on the left. Simplified way is you essentially take your PDE, if it's of this form. There is something that people have known in mathematics where you can say, you can transform this into a backwards stochastic differential equation, and there exists a backwards stochastic differential equation such that it has the same solution as your PDE. And that's really useless because the analysis tells you nothing about what that function would be. It just says that a function exists, right? So what do you do in this case? Well, you say, let that unknown function be the neural network. You parameterize that neural network. And now what you get out of this is you get a stochastic differential equation with a neural network embedded with it, and you will know it's the correct one when it satisfies the conditions of the backwards SDE, which is then just your loss function. And so you find that backwards SDE that satisfies, you find the neural network that satisfies the loss function, and you have a solution to the 1,000-dimensional PDE in terms of just training a neural stochastic differential equation. So now a 1,000-dimensional PDE is just about training a neural network within a system of 1,000 SDEs. And that is something that's now doable. It only takes 1,000 times 64 bits to be able to have one array of that size. It's now something that's actually possible to do on a computer. So using these kind of neural differential equation techniques, right, you can basically take methods where, let's say you know how Green's functions work, right? Now you go to an equation where you don't know the Green's function. You can parameterize that Green's function with the neural network. And if you have a neural differential equation solver, now this is a way to be able to approach that problem that might not have been approachable before. So what we've built is this diffeqflux.jl, which is a unified framework for for training neural differential equations, and it allows you to do a bunch of the things that you do with normal differential equation solver software, except now you put the word neural in front of it, and it makes the machine learning people in the department happy, but it also allows you to solve all these real engineering problems using these new types of techniques. Right, so we're trying to showcase how this gives you, data efficient machine learning, so data efficient training of these systems, but also a way to be able to accelerate solving differential equations themselves. Right, so you can accelerate the way that you solve PDEs by transforming it through these kinds of techniques. So that's that first section. So I love the neural differential equations, but what are the other things that we're doing, right? So one of the things that we're doing a lot with is this modeling toolkit, which is an open source compiler and IR for models and transformations. So the reason why we're starting to look at transformations is because, well, at first we thought, we can do everything we can. We want to do everything with numerical methods, right? So my research was based around, implement every single numerical method you can, find out what's different between them, and use that to find out what you need to do to make new numerical methods do better. But what we found out is, especially with talking with Hilding, you can't solve everything at the numerical level. Some things have to be done through through symbolic transformations. So what we needed to do is we needed a platform so that way we could just start implementing all of these program transformations to be able to research how these methods work and try to come up with new ones. And so our defining principle was really that instead of trying to build a language, right, you guys could build the languages, you guys are all using the languages. Instead what we'll do is we'll define a model transform, right, we'll define an IR and document this IR. This is how you represent this type of equation. And then a transformation is just a compiler pass from this IR to another IR. And so you can say this is now, and you also allow this IR to have high-level context about the systems, right? The kind of context that you need in order to do the symbolic transformations. And on top of this, anyone could build a domain-specific language. But this is what we'll leave it as. We'll leave it as this is the IR, right? So normally when you're building something like a Modelica, you'd have to build one of these intermediate representations in here. Now we'll say this is our interface, so just because we want to start hacking on how transformations work. Right, so here on the left, I kind of just showed this is what it's like. Some people in Jubilee actually use this as an interface for building models. So you just kind of say, here are my variables, equations, and generate a function, right? So that's what it's like. So now we have a compiler that we have a representation for models that we can then start hacking on and start trying to understand how the symbolic methods work. And one of the things that we got working very early on, which is interesting, is that if you treat your symbolic variables, if you treat your symbolic types like they were numbers, and then you tell the Julia compiler to treat them like they're numbers in every single function that they go into, then they will work in functions that you've never actually defined. So here's an equation where this is how a user gives us an ordinary differential equation for numerical solving. And we say, well, I don't want to deal with it numerically, right? So what you do is you take modeling toolkit and you put these variables in there, and then you trace their function and you get out their numerical function as a symbolic function. So this is a full example that works out. You give me a numerical function, I turn it into one that's symbolic on the fly, I use that to compute the derivative, the Jacobian, and then I can give you back your symbolic Jacobian from your numerical function. So now you don't even have to ask people to use your DSL. You just say, well, if you've ever written a numerical function, I can turn it into my DSL so I can start using your models to play with. So that's a fun little feature that actually kind of comes for free just by pushing through the compiler this idea that my symbolic operation type is just a number. And now what our current research is in doing things like trying to understand how different algorithms, or different ways to represent high-level algorithms. So for example, what I'm showing on the left here is, here's a way of describing a PDE system which is discretization independent. And then we can have other packages. So we actually have many different groups in Julia that are writing these discretization systems so that way they can say, from this PDE, here I'm going to do a finite difference discretization on it. And it kicks out an ODE problem that the ODE solver can solve. But someone else can then add a discretization dispatch that says, oh, discretize it like a finite element method, discretize it like a pseudospectral method. And so we're using that to be able to understand, if you can have one code where you change one line to be able to change to all the different PD discretizations, what can you start finding out about the efficiencies of these different methods in different contexts? Other things that we're looking at are, for example, model order reduction, since now we have this formulation, and we have this idea of just everything about the IR is just writing a compilation pass from one IR to the next IR. Model order reduction is one of these forms, which is just a compile pass. And so how do these linear methods do? And another thing that we're looking at in that sense is if you replace a giant portion of your equations by a neural network, right, now you have a form of a nonlinear model order reduction, which is in the form of a neural differential equation. How does that compare to linear model order reduction methods when they're done at scale? Right, so we're looking into a lot of these different ideas of how you can mix the symbolics and numerics, especially mixing symbolics, numerics, and neural networks together. And now for the last part, let's just assume that your differential equation is good, right? So let's assume that if you wanted to put neural networks in there, you did. If you wanted to, do tearing and, DA index reduction, all that, you end up with a system that you actually wanted to numerically integrate. At this point, is there anything that we can do on the numerical side to improve the solving of the equations that are given to us just as numerics? And what I really want to show is that you can even make non-stiff methods better, right? So non-stiff methods are still being improved in 2019. How is that the case? Well, so if you take a look at your Runge-Kutta methods, right? So you learn RK4, all these, but there's a more general structure to the Runge-Kutta method, which is it's just a loop of adding number or taking values of the derivative to be able to extrapolate in the future and get another derivative value, and you keep on putting these together, and then you do some linear combination between all your derivative values. And so you can get this table, which is a Butcher tableau, and you can understand that this table of numbers represents my Runge-Kutta method, right? And there are many ways to judge a Runge-Kutta method. So what you can do is you can say, I have a fourth order method, so what are the fifth order coefficients? Well, the fifth order coefficients, you can actually write them down, and you say, well, if those are the next terms of my Taylor series, I want them to be as small as possible, because then those are going to be the main terms of my error. Another thing that you can look at is the stability of the method, right? What is the largest step size that you can take given certain eigenvalues? And so for a given Runge-Kutta method of, say order 4 or 5, you can fill any real numbers into that table, and you get a different next order error coefficients, and you get different stability. So the question is, what is the best numbers that you can choose? Well, of course, there's going to be a lot of things that you can choose, and they'll have different ups and downs. And so the one that people chose back in the 80s was just, the Dorman-Prince method, which is these coefficients, where what they did was, at the time, they didn't have really nice computers to do global optimization, and so they just zeroed out this area right here to be able to say, well, this makes the optimization easier to do by hand. They did a few hand calculations, so that way they got rational numbers, and then they found out what the other coefficients had to be given the order coefficients. And that was done in 1980. You know that as Dupree or ODE45, and you're still using that. For the most part, unless you're in Julia, because what happened was people later in like 2013 found out that, hey, you don't have to make this assumption. We don't have to make everything rational numbers to make it easy. We can instead run global optimization to be able to find out what the best coefficients would be to minimize these error coefficients. And so there have actually been some very recent methods. So the ones that we showcase in our tutorials, like the SIT5 method, has about, I think it was a 20% smaller error coefficients, and that does kind of correspond to larger step sizes in real user code, and that does mean that it's small efficiency gain. It's nothing huge. No one would probably ever give you an academic grant for speeding up non-stiff solvers by 20%. But what it does mean is that everyone's code is sped up by 20%, and there's a lot of people who use that, and so that's something that we really should be making use of. And also, there's even larger gains that are had with some of the higher order methods. So Werner in 2013 also came out with these 7th order, 8th order, 9th order methods, which used a lot more of these global optimization techniques to come up with better coefficients. And how much better might these be? Well, if you take a look at, here's the error, here's the time, and so if you take a vertical line, this is the amount of time it takes to solve the equation with the same accuracy with different methods. You can see that this 9th or the 7th order Verne method can be about 10 times to 5 times faster, just because they've really optimized the coefficients a lot more. And this is, the Werner is actually the same John Werner who created a lot of these methods all the way back in the 80s and 90s, but he's just come back with these newer optimization techniques and really optimize the coefficients more. And if you go from equation to equation, you can see very consistent results that these higher order Runge-Kutta methods with more optimized coefficients will give you something that is, a more optimized solution. So these are recent things that are not even embedded in most software yet. This just sits in there in the literature, and so everyone goes, yes, the academics are done here because they found out that there's a better method, and so therefore there's nothing else to do. But of course, you probably want that in your software instead of the older method, right? So another thing that's out there is that parallelism is really not well explored. Jubilee gives us this nice trick where you have this broadcasting syntax. So in MATLAB, if you do dot star, it does element-wise of A times B. But in Julia, what it lowers down to a map, where it's a map of all of the functions which are contained, built inside of a single kernel. And so this kernel fusion is not something that is just nice for making loops a little faster. But what it means is that if you've overridden how element-wise, what it means for this equation, right? So if you just say element-wise means do this on an arbitrary function, then the entirety of our ordinary differential equation solver will recompile to use your definition of element-wise. So that means that if you define an array type such that your element-wise performs the element-wise operation on the GPU, then this code automatically recompiles to work on the GPU. If you've written an array type so that way it works on through MPI, and through MPI it communicates between multiple GPUs, then this is something that will automatically work between multiple GPUs through MPI. Right? And so this is something that we've demonstrated with the Klima climate model, because this code, which just exists as the standard ODE solver, is something that they've now been able to put inside the climate model, and just by defining an array type, it's able to recompile to be able to be heterogeneous, give you heterogeneous parallelism. So this is one nice thing that kind of comes for free. So now you have 300 methods with free parallelism. But is there something else we should also be doing to be able to improve the parallelism that we get? And the answer is yes, because this requires that your arrays are really large. And so if someone doesn't have very large systems where it makes sense to parallelize through the array operations, what are some other things that you should be looking at? Well, it turns out that one of the authors of this stream, so Ketchison in 2016 made this picture, but this is actually a recent implementation of one of Klaus's earlier algorithms in 1994. So I'm happy to finally meet the people who've kind of done this thing. One of the things that you could do is extrapolation methods can be written as doing Euler's method with different step sizes and then adding them together. Well, if you're doing Euler's method with different step sizes, you can put different step sizes on different computers and then just add them all together by sending it all back. Right? So the extrapolation methods are methods that can go to infinite order. You just choose a really high order and you can get a lot of parallelism. And the same idea applies here where, by getting a higher order, you can say that, well, I get more accuracy, but if you don't want that more accuracy, then you just increase your step size and you make that a way to be able to parallelize more. So this is something we've been exploring. We haven't had all these great results yet. So one of the things that happens here is that the extrapolation methods are equivalent to a Runge-Kutta method, but they're equivalent to a Runge-Kutta method without optimized coefficients. So what might we want to do instead of just doing that naive thing? Well, you might want to start creating Runge-Kutta methods which are specifically made to be parallelized. And the way that you can do that is you can zero out areas of this column, so that way the first value has to be computed in serial. Then you can compute these two at the same time, these two at the same time, and then you do a linear combination of the results. So that'd be great, because this would be a Runge-Kutta method which is optimized specifically for dual cores. So you can do this where you can say, let me create an optimized fifth order method for 4 cores, because most people have 4 cores, maybe 8 cores, maybe 16 cores. So it would be great to just go do this, optimize the coefficients, and you get some really good parallel methods, and no one's done that yet. So that's one of the next things that we're doing. And if anyone wants to help us work on that, that'd be a great opportunity. So you could do this with explicit Runge-Kutta methods, and you can also do it with implicit Runge-Kutta methods, and it's just kind of waiting for someone to work on it. Another place that we've been looking at parallelism is through automatic GPU parallelism of a user-level code. So if you give us this numerical code, right? I keep on showing the Lorentz example because everyone knows it. So the Lorentz equation is nice and small. So what do you actually have in your computer when you have a GPU? Well, you have a accelerator card which has thousands of chips. So the one that I have with my computer is just a gaming level one. You can get it for $300, and you get 3,000 cores. All of these cores are maybe 10 times slower than the CPU, but you can run them all at the same time. So one level of parallelism is if your system is small enough, say less than 50 ODEs, well, then what you might want to do is take that ODE and you compile it to a .ptx kernel, and then you allow the user to solve 3,000 of their version of the ODE at the same time. So what are things that you can speed up by doing that? Well, what you can speed up are things like parameter searches, global sensitivity analysis, anything where they need to compute the same function with a bunch of different parameters. And now what we've been able to do is we've been able to automate that so that way any of the 300 existing native Julia methods, you can take that method and as long as it's GPU compatible, which they all are through that dot syntax, right? You can take any of those methods, you can take a user level function just written in Julia, and we'll take it and we'll automatically compile it to the GPU, so that way that you can then solve thousands of parameters at the same time. So this is a different level of parallelism, right? This is parallelism where you want to solve a lot of very small function, or a lot of very small ODEs, but it's another level that needs to be targeted, and we're seeing some very good results for, between 12 to 90x, depending on the difference between your CPU and your GPU, if you want to do these large parameter searches on less than 50 ODEs. It is only a method that handles smaller differential equations because you have to make sure that you don't overload the GPU registers, which are smaller than CPU registers. But if you do this, you can solve 50 ODEs, 3,000 at a time, and that's much better than solving 12 at a time or whatever you're currently doing on a standard node. So that was just on, those are just some things that you can do to make non-stiff ODEs faster, right? So the question everyone here probably wants to hear about is, how do you then go to stiff differential equations? And differential algebraic equations are just essentially infinitely stiff ones. So what I want to talk about are follow the BDF and what's coming to get Gears method, right? So everyone knows Gears method. It became, this magical method like VODE, CVODE, etc. What are some ideas for how to get around the efficiency that we found through that? Essentially, that software is very efficient. What are some ideas that might be more mathematically efficient that we just need better software to be able to tackle with? So let's take a look at the evolution of the method, right? It's basically as old as computers itself. You start with Gears method, but what they did was they used an adaptive order adaptive time method, and whenever they adapted their order, it would change whenever they adapted the time, it would change the time points in the history that you need to use. And so what they did was they just said, well, if we don't know the right points in history, we'll just use an interpolation to get those points. And ended up lowering the stability, and so Alan Hindmarsh kind of came and he updated the code by first adding root finding and Krylov methods, etc. But then they changed to this variable coefficient form that got rid of that issue with the interpolation. And since then, they've made this CVODE. So it's really been kind of one person who's taken the code all through these stages, and almost all stiff ODE solvers that you know of have kind of come from this series. Another one that kind of comes from the same series is Dassel, which is Linda Petzold was working with Alan Hindmarsh. Dassel or LSODA kind of is where Dassel kind of comes from, and then Dassel, so you go from LSODA to Dassel, and then Dassel is basically Alan Hindmarsh taking it back from Linda Petzold to put you put in the CVODE style, and now you have IDA, right? So all these methods are pretty much the same people, the same software, just small variations as you go through many histories. So how come no one has been able to really beat that? It's really more about the software engineering than it is about the method. Because the method, if you actually look at its properties, it has some major issues. So, for example, if you look at the BDF method, it's actually only A-stable. Well, it's L-stable till second order. If you get above second order, though, it loses its A-stability. And so a lot of times, if you actually take a look at what's going on in your BDF code, if you make CVODE give you out what every single step looks like, it's actually taking very small steps. But the reason why it's doing well is because they've really engineered how they're taking their Jacobian, right? So earlier we heard about quasi-Newton steps. Well, what the BDF method, what CVODE is doing in the background is if it will use the same Jacobian between different steps, assuming that it doesn't change very much, and because it's taking very small steps to be able to handle the stiff equation, because it doesn't have A-stability all the time, then it's able to just get less Jacobians, and it's able to be faster than most naive implementations. So that's probably not the thing that you thought you'd hear, right? You probably hear that BDF would give you really large time steps, but actually one of the reasons why it does really well is it takes really small time steps and uses that effectively. So the other thing that kind of happens is every time you have an event, it has no more history. And because BDF methods need history in order to have higher order, what it does is it restarts and it decreases the step size, and then it has to do its restarting process over again. So here I'm just showing a bouncing ball, so a completely non-stiff ODE, which you can solve till time infinity in basically one step. But no, BDF method, it does an Euler step, then it does a trapezoid step, or a BDF2 step, and it does a third order, fifth order, and then does a few fifth order steps, and you hit an event, and now it has to start that process over again. It has to go to Euler, trapezoid, et cetera, and then you go all the way to the next one. Every time you have an event, it throws away the history and has to do smaller time steps again. Now, because it's able to reuse the Jacobian between those steps, it's not as bad as as something else, but it still needs to do the linear solve process with that LU factorized Jacobian. Whereas something like a Rodas 5 method, with a fifth order Rosenbrock method, it doesn't need history, so it just kind of steps from event to event, and as long as you have a good enough interpolation, you can get all the values that you need within the interval with the full third order, fifth order, etc. So what we've actually found is that if your system is small enough that these Jacobian reuse properties of the BDF method don't come into play, then getting a new Jacobian every single time to use a high-order Rosenbrock method is actually a lot more efficient. So the bottom lines here are these newer high-order Rosenbrock methods. They're not really newer. It's just I don't think anyone's ever implemented the fifth-order Rosenbrock method because it only shows up in one of Ernst Herrer's master's students' theses, which are not really online, so you kind of have to go digging for it and find it. But if you do find it and you implement it, it's a great method. For small enough systems where Jacobian reuse isn't a major issue. So what do these methods kind of look like? Why is this kind of a factor? Well, the Rosenbrock methods they have the structure where it's a right side, then linear solve, right side, then linear solve, and then update. It's equivalent to what you would be doing with an implicit Rackauckas method, except you aren't actually solving an implicit equation, you just have a linear equation that you have to solve each time. So if you actually had to iterate that linear solve a few times with the Newton's method, that's how you kind of get the equivalent Newton method to the Rosenbrock method. So because it's not actually solving a implicit system, that Jacobian has to be accurate, so you have to recompute it each time. But because of the way that this method is set up, it's essentially a Rackauckas method with a few linear solves in there, so that way it could be stable. And so then what you can do is you can say, what's the fifth order method with the most efficient coefficients, so that way it can take the biggest step size possible to get the least error, etc. It's the same problem as the Rackauckas methods. And then someone has optimized the fifth order Rosenbrock method, and it gives you good results as long as you're able to compute new Jacobians every single step. Right? You can still lose out to CVODE because it's reusing the same W that is factorized from before, but as long as W is small enough that the O of n squared factorization doesn't take over, this ends up being more efficient. And so now what are some other things that you can do to get around the supremacy of BDF for some cases? Well, you can say, I'm not going to just solve an ODE, but I'm going to solve specific cases of ODEs. Right? I'm going to look at second order ODE problems. So second order problems have a structure that a lot of them end up having, they live on symplectic manifolds. They can come from Hamiltonians. Other things that you can look at are split ODE problems, which is, here instead of just giving you an F, I can give you an F1 and F2. So that way part of it can be implicit, part of it can be explicit. You can make that list of F1, F2, F3, etc. go on as long as you want as well, as long as you have a solver that specializes on all that information. You can say that I can split it, but also have part of it be linear. Or I can split it and have part of it be linear, but also the linear part is going to be acting only locally. So that's actually what you see in a lot of PDEs, right? A semi-linear PDE actually gives you all this structure. And so if you just say U prime equals left, F, you're basically throwing out all that information, and then you're not solving it as fast as you can. Right? So if you split up your ODE solver and you say, these are all the different ways that you can start giving me methods, what are some things that you can start doing? Well, then these methods that a lot of people think of as for PDEs actually become a method for very simple forms of ODEs, right? So exponential integrators you can think of as an integrator for a semi-linear ODE, which is an ODE where you have a linear part and a nonlinear part. And these methods were first developed for partial differential equations, but they let you essentially get the analytical solution to the linear part and then only have to deal numerically with the other part. And so one of the questions that we've been thinking about is, can you take an equation, if someone just gives you an ODE where they give you the two parts together, can you find out, can you use one of these tools like Modeling Toolkit to find out how to divide it up for them such that you can get a more efficient solving method? right? So we're looking into these kind of, this is where there's this crossover between more numerical methods and more symbolic methods, because you kind of need to do both accurately in order to get the best methods going. And so what our current results are, just in case you're curious, is that somewhere around 20 to 30 stiff ODEs, these higher order Rosenbrock methods do very well, right? We've been able to optimize these, and these ones that really only exist in the Julia language are really what are doing the best there. So non-stiff equations, we have these Werner methods and such. For stiff ODEs, these higher order Rosenbrock methods do well, and we have very recent benchmarks which are showing that optimized S-Dirk methods, which are an implicit method where we're using a Jacobian reuse technique, which is more like Raddau. In these cases, for less than 2,000 ODEs, we found that these methods have now been the newest optimized ones. So these are former Runge-Kutta methods, which have been optimized. And then when you get to above 2,000 ODEs, we still have this unhappy face because we can't beat the old sundial BDF there, but this is an ongoing research problem to find out what are the things about sundials that's making it do well here, and how can we instead just start improving different methods to see if we can get something better. But even in that case, right, we still find that there are different methods where in very specific cases, which are commonly used, there are better methods than BDF. So in a lot of PDE contexts, what we found is that there are these stabilized explicit methods, like the ROC method, so ROC2, ROC4, and there was one that was eCirc, which is just published in August 2019. Those methods actually end up being better than the BDF method in these PDE contexts because you don't end up having large complex eigenvalues, and that's one of the limits on the stability. So if you allow yourself to limit the problems you're going to solve, you can build a method which is specifically good for that case. And also, if you know of a good split for your equation, then IMEX methods tend to do better than the BDF. But if you don't know anything about your equation, then you kind of have to fall back to there. So there's still a lot of ongoing research that we're doing to be able to try to crack the code of what is the best method for all these different cases. But what we've kind of built is a research platform to really investigate this in all the different dimensions. And what we're really trying to do with this, and some of the Julia users kind of are happy about this, right? So this is a feature I never use, but then whenever I get an error report, I see that this is getting a lot of use now. That what the user does is they just say solve problem, and we pick an algorithm for them. And what we end up doing is like, if you've given us any information on whether your problem's stiff, well, if it's unknown, then we can use methods that are auto switching between Runge-Kutta methods and Rosenbrock methods. If it's a certain size, if we know if it's larger than a certain size, then we switch to ES-Dirk methods. So we basically have a poly algorithm now that says if you give us nothing, but you want to have this equation solved, we can find an algorithm for you because of all the benchmarks that we have in the background. And so we're trying to improve this, and also we're also looking into whether we can have a neural network choose this, mostly for fun. But these are things that in the end we think that we can abstract away all the, we want to find all the subtleties to find out what the best method is for every case. But in the end, I think that we can take that away from the user and say, well, you don't really need to specify the method anymore because we've done enough benchmarking to know what's going to do well here. So in conclusion, today you can solve differential equations, and tomorrow I very much hope that you'll be able to solve them much faster, right? So there's a lot of things that we're doing. We're going to be embedding neural networks within methods to be able to solve 1,000-dimensional PDEs, right? So that 1,000-dimensional PDE example solves now in 5 minutes on a laptop. So that's one of these changes where using these entirely new methods can really change what is possible. We build a compiler so that way we're able to look at how these different techniques like model order reduction, what happens when you do them on these systems, how do they compare to neural network model order reductions, and this is now becoming one of our new research areas. And then we're just continuing to improve the numerical methods. So we have a whole team in the Julia DiffyQ ecosystem, which is all dedicated to, we want to solve these things fast. Everything is written in pure Julia, so everyone who knows the language can then just hack on all the different areas and start playing around with what happens when you change all the different pieces. And pretty much daily or weekly, we have advances in different areas, right? What I've shown you here is just what we've talked about with ODEs, but probably most of the work has gone into new methods for SDEs and delay differential equations. And so you can basically read through that or join our chats if you want to learn all about the intricacies of solving a differential equation. And so I just want, I'm young and I'm just starting my faculty search, so I need to ask if you're a student and you want a paid summer position and you think that differential equations are cool, and everyone says that they have positions for machine learning, well, I'm the one person probably that's telling you that you can work on differential equations if you want, and so you can contact me for Google Summer of Code. So if you want a paid position in the summer where no Julia experience is required, but you will learn Julia and you get to hack on these differential equation solvers, maybe try to make one the fastest in this domain and write a really nice blog post that you've made the fastest differential equation solver for this specific problem, you can come talk to me and we can get you set up with one of these positions. And if you're in the industry and you're interested in this research, we are trying to get a CSSI grant together, which is a grant for the Julia DiffyQ software ecosystem, and it's open source tools for differential equations. And what we're really looking for is industry support to basically be able to say, yes, industry actually cares that this research is being done. Right? The academics kind of think that making ODEs faster is not something that anyone cares about anymore. No one cares about DAEs. Everything's all stochastic delay differential equations now in academia. But what we need to do is we need to get support from industry to be able to say, no, people actually care if you make a DAE faster. So please come talk to me if you want to give us a letter of support. So thank you very much. Hopefully you think that a lot will come for differential equation research in the future.